after a lot of time working on learning how to prove things, I decided we'd have a go at heading back to the art of computer programming and seeing where we get to. I will confess that I took a glance over the problems that I stopped on before we did this sort of side quest. And I managed to, well, I got sucked into one of them, and I did manage to sort of get the answer, or at least I understood the answer, which is good, because I didn't before. I really had no idea where to start. So this section, but we go back to the start of this section and read through this mathematical preliminaries bit, and then the mathematical induction section, which I think I will understand a little bit better now. I haven't covered the induction section in Book of Proof, so I'll probably return to some of that. But I wanted to give myself a little reward for all of my hard work and spend some time with Knuth's work. Hello, Woodberg. So, yes, that's what we're going to be doing. And let's see how far we get. Hopefully, well, I'll be able to work through at least one problem unless I've forgotten how to do it. So, yeah, let's get going. What am I even doing? Let's get rid of that. Okay. Mathematical preliminaries. This is the art of computer programming, by the way. In this section, we shall investigate the mathematical notations. Sorry, just messing around with my window here. Mathematical notations that occur throughout the art of computer programming, and we will derive several basic formulas that will be used repeatedly. Even a reader not concerned with the more complex mathematical derivations should at least become familiar with the meanings of the various formulas so as to be able to use the results of the derivations. Mathematical notation is used for two main purposes in this book: to describe portions of an algorithm and to analyze performance characteristics of an algorithm. Just two small things. We've had to do all this work to understand. The notation used in descriptions of algorithms is quite simple, as explained in the previous section. When analyzing the performance of algorithms, we need to use more specialized notations. Most of the algorithms we will discuss are accompanied by mathematical calculations that determine the speed at which the algorithm may be expected to run. These calculations draw on nearly every branch of mathematics, and a separate book will be necessary to develop all of the mathematical concepts that are used in one place or another. However, the majority of the calculations can be carried out with a knowledge of college algebra, and the reader with a knowledge of elementary calculus will be able to understand nearly all of the mathematics that appears. Sometimes we will need to use deeper results of complex variable theory, group theory, number theory, probability theory, etc. In such cases, the topic will be explained in an elementary manner if possible, or a reference to other sources of information will be given. The mathematical techniques involved in the analysis of algorithms usually have a distinctive flavor. For example, we will often find ourselves working with finite summations of rational numbers, great, or with the solutions to recurrence relations. Such topics are traditionally given only a light treatment in mathematics courses, and so the following subsections are designed not only to give a thorough drilling in the use of notations to be defined, but also to illustrate in depth the types of calculations and techniques that will be most useful to us. Important note: although the following subsections provide a rather extensive training in the mathematical skills needed in connection with the study of computer algorithms, most readers will not see at first any very strong connections between this material and computer programming, except in section 121. The reader may choose to read the following subsections carefully with implicit faith in the author's assertion that the topics treated here are indeed very relevant, but it is probably preferable for motivation to skim over this section lightly at first and, after seeing numerous applications of the techniques in future chapters, return to it later for more intensive study. If too much time is spent studying this material when first reading the book, a person might never get onto the computer programming topics. Gosh, wouldn't that be a shame? However, each reader should at least become familiar with the general contents of these subsections and should try to solve a few of the exercises even on first reading. Section 1.2.10 should receive particular attention since it is the point of departure for most of the theoretical material developed later. Section 1.3, which follows 1.2, abruptly leaves the realm of pure mathematics and enters into pure computer programming. A more leisurely presentation of much of the following material, together with related concepts, can be found in the book Concrete Mathematics by R.L. Graham, D.E. Knuth, whoever that is, and O. Patashnik, 2nd edition, etc. That book will be simply called C-Math, and we need to refer to it later. Hello, Alpha Victor Charlie. What am I doing? Well, I am reading through The Art of Computer Programming. I did study this section before, when we were working through, before we went on our sojourn to the Book of Proof, or Book of Proof rather, and now we are returning to it, possibly briefly, possibly for a more extended journey, to see how much of it I can now make sense of. How are you doing, by the way, Alpha Victor Charlie? Am I in the right category even? Yes, I'm in the right category. Good. Always good to get the category wrong. Okay. Let's wait for these people to pass. Mathematical induction, something that I did not understand very much about on first reading, and still have not really effectively studied at all. I have not proved anything by induction, but I have a feeling that knowing some of the basics of how proofs work will help me work through this section more effectively. I will try to describe what I've learned. I feel I have learned something. I can't quite determine what it is though. Sojourn. Sojourn. That's one $10 word I haven't seen someone use in ages in the normal day. Yeah, I suppose it is a bit unusual. That's a good point. Yeah. Well, maybe the lighting is terrible in here. One moment. That will sort us for a little bit, I hope. Okay. Yes. Okay. Onwards with the sojourn. Sojourn. I've just forgotten how to pronounce it now. Sojourn. Mathematical induction. Let Pn be some statement about the integer n. For example, Pn might be n times n plus 3 is an even number. Or, if n is greater than or equal to 10, then 2n, 2 to the power n, is greater than 3 to the power n. Suppose we want to prove that Pn is true for all positive integers n. An important way to do this is give a proof that P1 is true, give a proof that if all of P1, P2 through Pn are true, then Pn plus 1 is also true. This proof should be valid for any positive integer n. Alpha Victor Charlie says, so you're a cross between a maths/CS/literature guy at once with a good amount of philosophy peppered in. I did do an arts degree. One of the reasons I have to study so much maths now. So there may be something to that. Sorry, terrible microphone usage. Yeah, I need to watch the Angela Collier video on Steam. It's on my watch list. Full of steam on this channel. Okay, okay. Leave it alone, leave it alone, leave it alone, leave it alone. Okay, that's fine. Right. I just can't leave it alone. Okay. That's better. That's better. Cross keys. Nice username. Hell yeah, the BA to dev pipeline. Truly the most cursed of paths to walk. BA for business analyst, or am I oh, Bachelor of Arts, of course. Wow, it has been a long time since I did my Bachelor of Arts. Yeah, yeah, yeah. Wow, I can't believe that took me a moment. Bachelor of Arts. Yeah, BA to dev pipeline. It was even worse for me. Well, it was sort of better. I was actually a sort of dev, like teenage coder to BA, to dev pipeline. Somewhat cursed, also. So when I was first reading this chapter, I was like, with mathematical induction, this thing here. Wow, need to select the right thing now. Let's give myself a bit of green. This section here. I had no idea what this was doing at all. Well, I sort of did. Like, my basic idea is, okay, so if you can prove somehow, through some means, that if P1 is true, and then if you can sort of prove Pn plus 1 is true. I don't even know if I got this on first reading, if I'm honest. Then you can prove it generally. I think this is basically where I was starting from. There's all kinds of holes in what I just said, obviously. Firstly, of course, it needs to work. Like, this only works for positive integers. It only works for one. This particular incarnation, anyway, only works for 1, 2, 3, etc. So that's important to know. Of course, quite useful for computer programming because we're often just dealing with things like that. Now, this statement here, let me get rid of this. This statement here is actually far more dense than I initially clocked. So what is it saying? So this one, you know, okay, so we're giving a proof that P1 is true. Like the statement for the value of 1 is true. Okay, fine. Deal with that. Give a proof that if all of these are true, let's underline true just for fun, then this is also true. Ooh. Is also true. So it's like, and this should be valid for any positive integer. Okay. So it's like, it's an if then, and that means it's like a, it's like one of these, I think. I mean, it probably should look at the formalization of this, I suppose. So we want to prove that if all of these, like if it's true for every positive integer, then, so we suppose that it's true, then this is also true. So that's like kind of in the reverse of what I would intuitively expect. This is quite loud, isn't it? Okay. How's my audio? It's maybe okay. You can probably turn it down. Let me just tweak it just a little bit down. Okay, great. Krosky says, I'm old, and when I did university, they had figured out that web dev was going to be enough of its own thing, that it couldn't just be part of computer science, but they had no idea in what way or how. So I did BA in design for web and interactive media. Yeah, I'm familiar. Well, I'm not quite familiar with those degrees, but I remember those degrees. Assert PN, says Rook. Hello, Rook. Okay, so that's that bit. We'll need to reinterpret some of this, of course, as we go through. Okay, let's kind of move through. As an example, consider the following series of equations which many people have discovered independently since ancient times. Oh yeah. Okay, 1 equals 1 squared, 1 plus 3 equals 2 squared, 1 plus 3 equals 5 equals 3 squared, etc. We can formulate the general property as follows. 1 plus 3 plus some. plus 2n minus 1 equals n squared. Sum of n terms. Okay. So I guess that's 1, for example, 3, and then we've got, so n I guess is this 3. So if it's in the case of 3, it's 2 by 3 minus 1, which of course can be 6 minus 1, which is going to be 5. Okay. So it's all the odd numbers up to 5. Now, I guess, I mean, this is another way of saying, you know, a kind of familiar formula of an odd number, which is 2a plus 1. Is we've spent lots of time in the book of proof looking at this, so I guess this is the preceding odd number. Sorry. 2a minus 1. So it's not actually up to. It's not actually up to at all, now I think of it. It's just, it's up to the square of, well, actually it's not at all. It's not that at all. It's up to the kind of double of, it's up to the double, I mean, that's what this is saying, right? It's the double of this n, the number just below that. So the odd number just below that. Okay, interesting. Which Knuth book is this? This is The Art of Computer Programming, Volume 1. You can buy it. I would encourage you to buy it. Of course, we live in a world in which things are accessible in other ways, but it is available in PDF form. You can look at Knuth's website and he will direct you to the right place to buy a PDF, because apparently lots of not good PDFs out there. I bought it, as you can probably tell. I'm enjoying it so far, though. Not that I've got to spend as much time with it as I would really like. Okay, so we've got the general property. Let us, for the moment, call this equation Pn. We wish to prove that Pn is true for all positive n. Okay, so let's try and kind of just muddle around with that. So how do we put this with like a suppose? What is it? Proposition. It's essentially for a positive integer, no. Well, positive integer n. N squared. Oh, terrible writing there. N squared equals. Oh, terrible writing again. 1 plus 3 plus etc, 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 all the way up to 2n minus 1. Right, so with the proof techniques I know, which are direct proof and contrapositive proof, although I barely remember that, so I will need to revise that. I do not have the mathematics to prove this thoroughly right now. Obviously it's on the screen so you can see it, but I'm not looking ahead. I don't have the mathematics to prove this thoroughly because I don't really know, like, I mean, the only kind of way I know now with direct proof is you need to sort of, I don't know, you need to like transform n squared into this form maybe. And I'm just gonna get nowhere with that. I mean, you could sort of try with like, if it's n squared, That's sort of the same thing as saying like a bunch of so, I mean you just get like nowhere with that. Yeah, so don't have the techniques. Now if I was to like use my very like knowing nothing about induction, like we could say we want a proof of, I'm not going to try and do this rigorously because I don't have the skills really, but let's say we'll start off with like thinking about, what are we calling this? P, right? P1. Now in this case, let me actually put this off to the side. It's not a 7. It's not a 2. One of the horrendous things about being in computing in this current moment is you just think, handwritten digit? Is that, what is that? Is this too much like a 7? Anyway, just feel for the algorithms, you know? Nope. Okay, come on. Just move on. All right. So in that case, we would have, we could just plug in 1, right? So we would say 1 squared equals, and we're just going to have, well, I mean, how do we even expand this series? I don't even know. But like, let's just try doing this also on the side. And we end up here with, sorry, no, not right, just making mistakes. This is going to be 2 minus 1, and this is going to be 1, obviously. So this is going to be 1, and then 1 squared is obviously 1. So, you know, we have our proof of P1. Now, this other thing, we've got like, then it goes something like, we're thinking about the way the proof is structured. It's like, I've seen it, suppose that all of yeah, and then we do something where we need to show that if these are all true, that will imply that P n plus 1 is also true. That part I'm not don't have a lot of facility with that. But perhaps I will be able to understand Knuth's working through of it. Now if I was to try to just do this very naively, I guess I could try to frame this in terms of P1 maybe? I know what P1 is, so can I put P2 in terms of P1? I could possibly try, or I guess really I want to put it in terms of like maybe Pn minus 1. Yeah, I also learned that relatively recently. Knuth, yeah. Yeah, so we could derive from well, anyway. Let's leave it at that and look at what Knuth does. Okay. Okay. Great. So got the same thing for A. For all of P1, if all of P1 through Pn are true, then in particular Pn is true. So equation 2 holds. Equation 2 is Or is that just in... Oh, right, this is the equation 2. Fine. Right, okay, so it's on this side. It's on this side here. That's where that's put through. Okay. Thank you for the bits to enlarge your favorite emoji, Woodberg. It's always nice to see that in the chat. Okay. Right, so in particular Pn is true. Well, that, yeah. Okay, so let's say that series is true. Pn is true. So, given that we think all of those things are true, we're supposing that. So the equation 2 holds. So we can use that equation. Adding 2n plus 1 to both sides, we obtain... Okay, here's where it gets interesting, I guess. Alright, let's try this. Sketch this out. 1 plus 3 plus a bunch of stuff plus 2n minus 1 plus 2n plus 1. Okay. Great, so we got that on the left. That's fine. Now, well, I guess on the left, you know, it's not necessarily got a right and a left, but let's say this is equal to the other side of it, which is n squared, so we've got that already, plus 2n plus 1 which is also going to equal n plus 1 squared because that's what this works out to, I guess. Like if we try and do this ourselves, we're going to have n, we're going to have 1 here and 1 here, and they're going to have to be plus, so, and then of course this reduces to this. Okay, fine. Which proves that Pn plus 1 is also true. So there's a lot, that's quite a concise way of putting it. So how does it prove that? Oh, wait, of course. Eureka, I say as Knuth does all the work for me. It proves Pn plus 1 is also true because this is Pn plus 1. Sorry, plus 1. Yeah, like this here, this here, this here. Not a very clear way of me putting it, but he's taken this equation, or this property, yeah, equation, he used that term, I need to look at that term. He's got the left equal to the right. No, wait, he's taken the equation, he's added 2n plus 1 to both sides, which gets this property here. He's reduced this side. Maybe I guess the other side can be reduced to it as well, to this. And this, of course, will be what we get if we try to run Pn plus 1, which, of course, is going to be n plus 1. Ooh. N plus 1 squared, which, of course, is also going to be 1. You know, etc., 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 all the way to, yeah, 2n. Well, it would be all the way to 2n plus 1 minus 1, which, of course, is going to be 2n plus 2 minus 1, which is going to be 2n plus 1. No, wait, that's not right. Where am I going wrong in this? 2n minus 1. Let me work this through again. 2n minus 1 here. Sorry, I know you're chattering away frantically in the chat. I will visit you shortly. All of my brain is currently saturated. Okay, 2n plus 2 minus 1. 2n. Well, it's going to be plus 1, basically, which is not right, but okay. Maybe it's fine. But I guess, I mean, it kind of is fine, because really we've ended up with, like, you know, this little surprising, I guess, but it kind of makes sense. Okay, so before I clear my brain cache, in what way does this make sense as induction? So the induction approach here is, if, assuming the series is true, assuming it's true for 1 up to n is an arbitrary figure, arbitrary number, arbitrary positive integer, I should say, then in particular Pn is also true. So equation 2 holds in that case. And we say that if all of, which will be this, right? Let's use some notation just for fun. Yeah, if all of, oh, terrible writing here, through to n is true, then Pn plus 1 is true. That's what we're supposed to prove. And then I suppose the logic of the induction is we could just say that n is, like in this series here, we could say that n is 1, and we know that this is true already because we've already said that. And then if we then know that P1 is true, and we know that this is also true, then we can say, okay, so given that this is true, let's put into that idea n equals 1, which we can then use to prove that it's true for n equals 2, which we can then use to prove that it's true for n equals 3, and etc., etc., etc. Okay, interesting. Okay, great. Wow. Exciting. Okay. Alpha Charlie, thank you for your kind words about my voice. I try to be calm, mostly successfully, though not always. And hello, Noob404. You do see proof by mathematical induction. At least you do on the left. Here's the missing step. Add 2 n plus 1 minus 1 to the left side and simplify it for the next step. You probably said that earlier, didn't you? Anyway. Okay, I feel satisfied by that. That was quite exciting. Wow, I definitely understand this considerably better than I did on first reading, which is what you would expect, right? Okay. Very exciting. Why is my bitrate so terrible? Let me figure out what's going on here. Has anyone observed any dropouts? Anyone observed any issues with the connection? I've missed one chat message, strangely. Weird. Okay, well, I'll try and keep that under control. Anyway, I think it might be the heat. Router's a bit troubled by the heat. Oh well, let's see if we manage to keep it rolling. Just hate to see a terrible bitrate. Let me save my log file, actually. Because I keep getting... Okay, they're all saved. Great. Right, Anyway. Wow, there's a whole inspector about this. I don't know if you get to know. I get so many wild tools available to me as a professional Twitch affiliate. It's hot here, by the way, in case anyone's wondering. Wow, wild. Wow, this is wild stuff. Okay, not very exciting for anyone else though. I shall review this later for my own enjoyment. Okay, all right. Okay, back to the maths. Stream dropped for 30 seconds? What? Oh no. Did I say anything? Was I about to say anything very profound, do you think? Alright, well, the VOD should capture everything anyway, in case anyone's desperately keen to see what I said. Okay. Right. Thank you, Model Lord. I appreciate that. You know what I could do? I could actually watch my own stream, couldn't I? I usually turn that off. Okay. I move my head. It's visible. Okay. We're good. All right. Oh. Hate connection issues. Hate internet issues. Really annoying. Okay. Focus. Don't think about the internet at all. Right. Oh, I'm still thinking about the internet. Okay. Just going to put that over there. Okay, sorry. Then I really will get back to it. Okay. Now, So we were looking at that, we were looking at that, we were looking at that. Okay, great. Gosh. Right, so we did that. We can regard this method as an algorithmic proof procedure. In fact, the following algorithm produces a proof of... let me just sort that out. Come on. There we go. Algorithm proof procedure. In fact, the following algorithm produces a proof of Pn for any positive integer n, assuming that steps A and B above have been worked out. Algorithm 1. Construct a proof. Given a positive integer n, this algorithm will output a proof that Pn is true. Okay, so we've got like an algorithm he's constructing here. Prove P1, set k to 1, and according to A, output a proof of P1. K equals n, question mark. If k equals n, terminate the algorithm. The required proof has been output. Prove pk plus 1. According to B, B is somewhere. I don't know where B is. Is there a B anywhere? Oh, yes, okay, so B is the second step of the inductive process. Okay. Inductive proof. According to B, output a proof that if all of P1 through Pk are true, then Pk plus 1 is true. Also output, we have already proved P1 through Pk, hence k plus 1 is true. Increase k by 1 and go to step I2. Okay, I'm not quite sure what he's doing here, but we may become clearer. Prove P1, k equals n, question mark? No, prove k plus 1, increase k. Okay. Alright, so we're starting, okay, so we're starting k at 1. And according to A, output a proof of P1. Okay, fine. If k equals n, n is... Right, okay, so this isn't to prove the thing in general. This is to prove that Pn is true. Where n is going to be an actual number. So it might be like P... I don't know, P23. And to then... Okay, so what he's saying is induction is... You could sort of construct an algorithm based on an inductive proof where you... I went away again. That is very irritating. Okay, let me sort this out. How long was I out for? Okay, let me sort this. Okay. Yeah, I get little bits going wrong, don't I? That's so annoying. Hate it when that happens. Okay. Alright, we'll see if that does anything. Okay. Oh, no, yeah. I see it. I see it. Right. Okay, I'm gonna listen to myself slightly. Alright. Yes, okay, so where was he? So... Yeah, so what he's saying here, I think, is if you've got a proof by induction, you can sort of produce a proof where you start off with the proof of where n equals 1, and then you can use this to produce a proof, sort of generate a proof almost, you know, where you got the proof of p equals where n equals 2 and so on all the way through to your thing. So that's the kind of the, how does he describe it? He's like algorithmic proof procedure. Okay. So it's to construct a proof. Okay, interesting. All right, I think I understand that a bit better now. Let me get rid of some of this noise here. And Rook says, using n equals k is how modern textbooks teach induction, introducing another variable. Aha. I see. Okay. All right. Great. Okay. We'll see how much further I get before my internet goes wrong even more. Okay. Since this algorithm clearly presents a proof of Pn for any given n, the proof technique consisting of steps A and B is logically valid. Got it. So he's sort of showing why the mathematical induction approach is valid. Oh, and then he says it's called proof by mathematical induction. So, okay, fine. So he's sort of just building that up. Okay, fine. The concept of mathematical induction should be distinguished from what is usually called inductive reasoning in science. A scientist takes specific observations and creates, by induction, a general theory of hypotheses that accounts for these facts. For example, we might observe the 5 relations in 1 above and formulate 2. In this sense, induction is no more than our best guess about the situation. Mathematics could call it an empirical result or a conjecture. Another example will be helpful. Let Pn denote the number of partitions of n. Okay. That is the number of different ways to write n as a sum of positive integers, disregarding order. Since 5 can be partitioned in exactly 7 ways, okay, I'm probably going to need some room here. We have P5 equals 7. Okay, so it's just different ways you can come up with to add the digits, positive integers together, I suppose, to get 5. Okay. Which is what he says. We have P5 equals 7. Yeah, fine. In fact, it is easy to establish the first few values. Easy enough, I suppose. At this point, we might tentatively formulate by induction the hypothesis that the sequence P2, P3, etc. runs through the prime numbers. Okay, I suppose we could say that. To test this hypothesis, we proceed to calculate P6. P6, and behold, P6 equals 11, confirming our conjecture. I suppose he's making the point that this is like the scientific meaning of the term induction, in that we've sort of we've got some empirical data that suggests that this is like the prime numbers. Unfortunately, P7 turns out to be 15, spoiling everything, and we must try again. The numbers Pn are known to be quite complicated, although I should learn to pronounce this name, it's going to come up a lot. Ramanujan succeeded in guessing and proving many remarkable things about them. For further information, see G.H. Hardy, Ramanujan, chapters 6 and 8, so he comes up again, and in another section. Mathematical induction is quite different from induction in the sense just explained. It is not just guesswork, but a conclusive proof of a statement. Indeed, it is a proof of infinitely many statements, one for each n. It has been called induction only because one must first decide somehow what is to be proved before one can apply the technique of mathematical induction. That sort of skips in my brain. It has been called induction only because one must first decide somehow what is to be proved before one can apply the technique of mathematical induction. What is he talking about? Surely that's the case with any proof. Okay, well, if anyone has any ideas on why he's saying that, do let me know. Henceforth, in this book, we shall use the word induction only when we wish to imply proof by mathematical induction. There is a geometrical way to prove equation 2. Somebody was mentioning this earlier. Figure 3 shows for n equals 6, n squared cells broken up into groups of 1 plus 3 plus something plus 2n minus 1. Is that happening again? Is that my connection messing around with me again? Alright, let's hope not. Rook says, you have to notice a pattern first before trying to prove it in general. Alphavit Shelley says, watch the trailer of the movie The Man Who Knew Infinity with Dev Patel and Jeremy Irons. It pronounces the name Ramanujan properly. Okay, I will make a note of that. Thank you. But always good to have a pronunciation guide. Okay, so you can't quite... You might not be able to see this, but in this diagram on the right, we've got actually, I probably want to make this a little bit brighter somehow. We've got these sorts of lines highlighted here. So, if we look at like a 9, for example, how many cells do we have? We've got 4 plus 4 plus 1, that's 8. Okay, whatever. Yeah, how does this prove it? I suppose... This is definitely 1 squared. This is 2 squared. Okay, this is 3 squared. Fine, okay, that makes more sense. 4 squared, 5 squared, 6 squared. And you can see it's squared, obviously, because it's a square. So, for example, if we look at... the 2 squared one... In fact, let's look at 3. If we look at the 3 squared one, it's got 3 rows, 3 columns. And we can see this is made up of 1 plus 3 plus 5. So it's a sequence of odd numbers. The final one being produced by... (2n) minus 1, where n is 3, so that's going to be 2, obviously 6 minus 1, which is 5. Okay, and you can see this is 5 cells because, well, we've got, I guess visually, we've got these 3. We could break this sort of, what do you call like the outline of a square? Like this kind of outline. We've got 3, and then we've got another 3 here, and we have to subtract 1 for this overlap. So it's a little bit actually like we've been dealing with in Venn diagrams and like intersect. There's a rule, right? Well, what is that rule called? The one where you subtract all the intersections. It's a bit like that. Kind of be an interesting way to work it through using that sort of logic. Let me try that at some point. Okay. However, in the final analysis, the picture can be regarded as a proof only if we show that the construction can be carried out for all n, and such a demonstration is essentially the same as a proof by induction. Okay, fine. Inclusion, exclusion, Bobbledon. Yes, that's right. Thank you, and hello, by the way. How are you doing, Bobbledon? I should apologise to everyone, by the way. I didn't stream on Thursday, even though Thursday is my normal day. And that was because I was not able to fly back from my destination due to fog. Fog destroyed my chances of streaming this week. Very sad. So I'm streaming today. Okay. Very well. Didn't get my streak going this week like I wanted to, but maybe next week. Maybe next week. I drew a little PNG tuber avatar though, which is very cute. Great. Oh, your stream. Yeah, I was wondering actually about streak. Stream. Next week. I'll be tuning in. UK rains and fog. Yeah, that's true. Yeah. Inevitable. Okay, our proof of equation 2 is used only as a special case. Our proof of equation 2 used only a special case of B. We merely showed that the truth of Pn implies the truth of Pn plus 1. This is an important simple case that arises frequently. That was occurring to me actually. I imagine there are other ways to think about that. But our next example illustrates the power of the method a little more. We define the Fibonacci sequence, f0, f1, f2, etc. by the rule that f0 equals 0, f1 equals 1, and every further term is the sum of the preceding two. Thus the sequence begins 0, 1, 1, 2, 3, 5, 8, 13, etc. I've actually been puzzling over the Fibonacci sequence a bit recently. Always a bad idea, but true fans of the project will recall that there is a notion in, let's say, systems programming, was a notion before I dispelled it, that, well, dispel is a bit strong, that if you have a dynamic array and you would like to, so dynamic arrays involve allocating a fixed size array, let's say for 2 cells. So let's say we allocate these for our array, and then somebody decides, some horrible programmer decides they want to add they want to add a third number. So we have to resize the array. So what we do is we probably need to choose some factor, and let's say let's call our factor q, and let's say it's 2. We need to decide, based on the size of our current array, what should we resize it by. So we can say, okay, we'll double it each time, hence the 2, and so we will then move our first 2 values into this, let's say this section here. Move our first 2 values here, and then we have more space for the third one and potentially a fourth one. And then if this happens again, we then need to allocate 8 cells. Great if I had a grid for this. 1, 2, 3, 4, 5, 6, 7, 8, let's say. So then we copy these 4 values into the first 4 slots here, and then there's space for a 5th, and then we can add more as we go, and we resize it then to 16 and 32 and 64, etc. Now, if you do it this way with 2, you can never reuse any of the previous space. So notice, sort of, no matter, I think I'm simplifying / remembering slightly. Let's say we get to here, right, and we want to, in fact, let's say we get to here and we want to resize into a length 16 set of cells. Provided that we would like to keep this static so that we can copy it out of. It doesn't matter how many times we double, we're never able to reuse any of the space earlier on. We essentially leave gaps in the memory. If you're interested in this problem, I've got a video about it. We essentially leave gaps in the memory, which is annoying and maybe not good. So there was a notion that the right value for q, well, let's say, in fact, let's use another trivial example. Let's say we made q into q plus 1. So in that case, I'm just messing around with my diagrams here. In that case, let's say we have a dynamic array of size 2. So we've got these elements here. We want to add a third one, but we can't because it's too small. We could then resize it to be 3 long. Copy everything in, and we get immediately full, so not a very great system. We could then resize it to be 4 long, and then we can resize it after that to be 5 long. So we could say, okay, let's say the 4 size array fills up. We now need to find 5 cells to put our size 5 dynamic array in. Turns out we have 5 cells earlier on. We got 5 cells here. So we can take this space that we used previously, that's currently a hole, put our values in it, and then we are reusing the space. And so we don't leave big holes everywhere in our memory, which is great. Possibly. So if you have this system, then it works well. Of course, it doesn't work well in lots of other reasons because you've got to do loads of copying. So the question is, what is the optimal value of q for dynamic arrays? Some people thought there is a sort of ongoing, like something somebody told you once, that the right value of q is e. And I can't quite remember the truth of this, but I believe, and again, go back and watch the video. The video, I wrote it fresh on this, is because this approximates the ratio of one Fibonacci number, if that's how you pronounce it, to the next. Actually, it's not probably like... The problem is if you actually try this out, because e is not an integer, you end up with it not really working very well. I think that's the problem. I can't quite remember. So I was thinking, one of the things that's been sort of charming me lately is, having done all of this mathematics, I can now work through mathematical problems in my head quite a bit better than I could before. So I've just been sort of doing that for fun in my head while I've got, you know, on flights or whatever. So I thought, well, maybe there's like a discrete version of E, and of course there is, which is, it's the Fibonacci sequence, right? So you could just use the Fibonacci sequence somehow for Q. And if you did that, maybe you would end up with something which worked perfectly. You would start off with, you know, 1 and then 2 and then what is it again? 3, 5, 8. Great. Everything works out in theory. At least in my head it did. I haven't actually properly tried this out. But it actually doesn't work perfectly because the fact that you have to keep the old array around while you're copying, like, screws everything up, messes everything up. And also, this is kind of hard to calculate, like not very nice to calculate this in like a very hot loop of your lower level system. Like, calculate the Fibonacci sequence like this is not very nice. E might be slightly better, or some approximation close to E might be slightly better. So, you know, it's like, not sure. All this is like complicated by real world factors and stuff like that. So I was wondering, basically, my challenge for myself, nobody, okay, I've just imploded my drawing system again. Let me just fix that. Come on. Again, just another weird glitch. Gosh, okay, everything's going wrong. Ah. Magic, magic, magic. Okay, alright, I think I'm still alive. Yes, so the question is, we like about the Fibonacci sequence, for this problem, we like that we can have 1, 1, 2, 3, 5, 8. We like the relation that this is the sum of these two numbers. That's what we like for the dynamic array purposes. But if we could imagine a sequence that would be better, what we would really like is a sequence that was the sum of these two numbers. So we skip one, because this one is going to be holding the list, the array, sorry. So we can't really use this space. So we'd really like this to be like the sum of the n-2 and n-3 terms. But, you know, it's not, obviously, you can't just, I mean, that sort of, you could do it this way, but then it wouldn't work further on. Yeah, so you kind of want a sequence which is like, you know, what is it? I minus 2. What is it? It's something like, yeah, anyway, you get the idea. So I've been puzzling away with that in my head. I might return to that, because if you come up with a sequence like that, and it's nice and it's easy to calculate, in theory you get the optimal array resizing factor. In theory. Might just be 1.5. I think my hunch is that it was 1.5 all along. But yeah. Coding bar. Wind noises and watching this Knuth Mathematica stream, yeah. Glad. The wind noises keep me in a cool state of mind. Alphabet Charlie says, so one of the problems I have with maths books in my school years was that they were just problems. Problems. Never went through... They never went through terse English text that would have helped. Is my PC making noise? Or server? I don't know. It's possible. Could be my fan. But you'd have to attend quite closely to, I think, to hear the fan. If you're hearing lots of stormy noises, that's just the background music. Bubbledon proposes 001 011 2 2 3 4 5 7 9. Yeah, maybe that's right. How do you generate that Bubbledon? Let's go 2 2 3 4 5 7 9, and I suppose it would continue with 12 16 21. It's not looking very charming for computing purposes, but maybe seems to pan out. 12 plus 16, that's 28. Start with 001 and then everyone. Yeah, it makes sense. Yeah, I just didn't get far enough to try it yet, but yeah. Starting with 001 makes sense. Yeah, and of course in reality we'd probably start like... There's another side of this, which is a lot of this makes a lot more sense if you round these up to the nearest like multiple of 8 as well. Just for computing purposes. Anyway, just getting distracted now. But I'm gonna take a photo of your sequence bubble and I will let you know in a future stream whether I manage to do anything useful with it. I hope so. Okay. We call it the Bubbledon factor. That's what I'll propose. Hello, Happy Nora. Math on a Sunday. I know. I was stranded in an airport on Thursday, so I didn't manage to stream. Very sad. Yes. And we're back to the art of computer programming, by the way. We're in it. We're seeing... Oh, you got your hair cut, Bubbledon. Oh, great. Now we're French sisters. Great. I did get mine done as well, actually. My forehead is so warm. That can happen. But nobody's going to see it, so... Okay. Right, Fibonacci sequence. Anyway, I got distracted. We will investigate it in detail in section 1.2.8. We will now prove that if... what's this? Theta? What's that symbol again? Theta, maybe? Theta? Something. Happy Nora, you're getting a haircut too? It's haircut season. We will now prove that if theta is the number 1 plus root 5 over 2, strange number, then Fn that's Fibonacci sequence number n, is less than or equal to theta, I suppose. Should remember the names of the... Let me just Google that before I totally ruin the stream by getting it completely wrong. No, it's not. It's not at all. What is it? Phi? No. What is it called? Phi. That is phi. Phi. Thank you. Rhymes with fly or pie. Yeah, phi to the n minus 1. Has it just messed itself up again? It has, hasn't it? Oh my gosh. I need to really do some debugging on this setup. There's that bug. I'm going to go through the logs for all this. Okay. Now this gives me an opportunity to try out one of my new tools, which I've been working on. It's a graphing tool. Okay, so we've got now. Can it? I haven't tested it against anything this dramatic yet. Well, let's see if it can handle it. I forgot to put Y on the front, which will be annoying later. Let me do that. I haven't got good text editing yet. We can see what this looks like. Okay. 1 plus square root of 5 over 2 x minus 1. Doesn't work very well. Maybe it doesn't graph very well. It does work for other things though. Let me just show you. I'll investigate that later. But look, I can graph. I can graph now in the thing. I was missing a parenthesis. Gosh, okay. Let me try it again. Okay, open. 1 plus square root. Okay, I missed that. Yeah. Square root 5 over 2, close bracket, x minus 1. Okay, well, we didn't learn that much from that, but still. It also defaults to a very small view, so it's not that good. But it's a start. It's kind of cool. I don't know. I think it's cool. You can also do you can do hashtags. I've been working on this. Yeah, uses a shader, uses shaders, and it does a little bit of uses a little bit of Math.js in there as well. I can move things around and everything. Anyway, that's what I've been playing with lately. So, right, for all positive integers n, so, you know, for 1, I guess this has got to be 1, right? Then I think it goes to 2, so, I don't know, anyway, for all positive integers n, call this formula Pn. If n equals 1, then f1 equals 1 equals theta to the power 0, sorry, phi to the power 0 equals phi 1 minus 1. Wait, so we're trying to prove that phi is the number. If phi is the number, etc., etc., we have fn is less than or equal to phi to the power n minus 1. Okay. 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 Happy Nora, you spoiled it. The golden ratio. It was the golden ratio all along. It's okay. I actually read this chapter before. I'm going through it again. Dunkable, just starting odes. Do you still add to it? I am adding to it very, very slowly. Is probably the best way to think about it. Yes, but the plan is to continue to add to it. Although I'm not getting through things very quickly. This is probably the most activity with the odes project on this channel at the moment, which is working through all of Knuth's The Art of Computer Programming. Okay, if n equals 1, then f1, which is of course going to be 1, which is going to be phi to the power 0, which is going to be phi Is he basically just saying here that what is he trying to say? Oh, he's trying to, okay, right. He's showing that this is equal. He's showing that it's equal, basically. Fine, okay. So if n is 1, then this is going to be phi n 1 minus 1, which is what he's got at the end. Sorry. And so he's showing that he's demonstrating this by saying if n is 1, then the first item in the Fibonacci sequence is going to be 1, which is going to be the same thing as phi to the power 0, because I think anything to the power 0 is 1. And then he shows that it's equal to this. Okay. 15 streams in a row. Wow. Happy Nora. Thank you for tuning in. And thank you, Dunkable, for your great username. And thank you for your thanks as well. Appreciate it. Okay. Now. You also get a lot of ones. You get a lot of channel ones if you hit 15 in a row. Feel free, just don't spend them all at once. Okay, so we've got the case in which n is 1. For step B, we notice that P2 is also true, since the second term is also 1, and that's going to be less than phi to the power 1, and phi to the power 1 is, yep, kind of plugs in here again, because we've got this 2 here. Okay. And it's going to be less than 1 because, well, I suppose we could just look at it, but yeah, that's probably the best thing to do. But I'm not going to look at it right now. Now, if all of P1, 2, and through n are true, and n is greater than 1, we know in particular, so this is the operative part, Pn minus 1 and Pn are true. So, Fn minus 1 is going to be less than or equal to phi to the power n minus 2, and Fn is going to be less than or equal to phi n to the power n minus 1. Adding these inequalities, okay, so we add the inequalities. Because I guess if we've got a, again, I'm not massively big on it, like I'm not a big inequalities knower. I suppose if this is the case, then we can also say that this is true. So we can add inequalities in that way. Okay, fine. Great. So we add them. Right, okay, so because of the way the Fibonacci sequence works, we can add the previous two terms to get what n plus 1 is going to be. So we add the inequalities, meaning we add these, and then he presumably does some little bit of work here to make this work. He's got phi to the n minus 2 multiplied by 1 plus phi. Now, this happens in a later exercise, so I think there's some ordinal stuff going on here. He's extracting. Now, the best way I've found to understand this stuff in this book so far is to try to put it the other way. So, I don't even draw this character. Phi n minus 2 1. I'm starting to see it now, I think. Gosh, I would love to be able to just see this stuff jump out at me. I assume I will one day. Yeah, and so then you can expand this to be n minus 2 plus yeah, you can do this. Now, another way of putting this is to say this is phi to the power 1, and this is phi to the power n minus 2. And if we are multiplying two things which are the same number to the power of something, you add them. You can add the exponents. So you can then say n, well, I guess it's really 1 plus n minus 2, which is going to, of course, be n minus 1. So all of this kind of, simplifies out to be... How do I do this again? Oh yeah, here we go. This, which of course is what we have here. So not immediately obvious to me that this is equivalent to this, but it is. Somehow, I mean, with these proofs, right, you never know. I mean, Knuth probably just picked this stuff out of his head, I imagine, but often the actual working out has to happen in reverse, right? Then you write it up in a way that makes sense going forwards. Life can only be understood backwards, but must be lived forwards, or the other way around, or something. Okay, so there's that. Great. So we get that inequality. The important property of the number phi, indeed the reason we chose this number for this problem in the first place, is that 1 plus phi is equal to phi squared. Plugging 5 into 4 gives fn plus 1 is less than phi to the power n. Okay, well let's try plugging 5 into 4, shall we? So where are we plugging it in? Probably here, right? So fn plus 1 is less than or equal to phi to the power n minus 2 multiplied by 1 plus phi. Now, we have this identity, I suppose, property, whatever it is, here, which is great. We can just take his word for it on that and replace this with phi squared. And as before, since we're multiplying these, we get to add the exponents together. And so we get phi to the power n. Because we've got n minus 2 and then 2 here, so obviously n minus 2 plus 2 is going to be phi to the power n, which is kind of cool. Mathematicians like to call it an equation. Okay, great. I've heard that term somewhere before. Yeah. Okay. Plugging 5 into 4 gives this thing, which we've just seen, which is Pn plus 1. Is it now? Yes, it is, because... Yes, because if we were to plug this into 3, if we were to look at 3, for example, then we've got Fn plus 1, we've then got phi, and then we've got n plus 1 minus 1, which is going to be, of course, n, which is this. Okay, great. So step B has been done. So we have proved... Yeah, well, yeah. We've proved that supposing P1 through Pn are true, and n is greater than 1, and it's an integer, we know in particular that, yeah, so we then prove that in that case, assuming that's true, then Pn plus 1 is true. We've sort of transformed one into the shape of the other. Okay. Or maybe not. Anyway, it makes sense. So step B has been done, and 3 has been proved by mathematical induction. Okay, cool. I can buy that. Wow, it's so much more fun when this makes sense. Fun to compare this stream against the last time I went through this material, and none of it made any sense to me. Okay, notice that we approach step B in 2 different ways here. We proved Pn plus 1 directly when n equals 1, and we used an inductive method when n is greater than 1. Okay. This was necessary since when n is 1, our reference to Pn minus 1 is 0 would not have been legitimate. Yeah, okay. Actually, P0 does happen to be true in this particular context, but we weren't asked to prove it, so we didn't. Yeah, okay, there's some sort of gotcha there, I guess. I don't know if that's true of mathematical induction in general. That's learning, baby. True. Yeah, that's... Yeah. I think that's kind of obvious, which means that it's probably not obvious. Okay. Mathematical induction can be used to prove things about algorithms. Consider the following generalization of Euclid's algorithm. Algorithm E, extended Euclid's algorithm. Given two positive integers, m and n, we compute their greatest common divisor d. We also compute two not necessarily positive integers a and b, such that am plus bn is equal to d. Okay. Initialize. Oh yeah, I remember all this. Set a tick. Yeah, he's got some... I've forgotten his notation now. Set a tick b to 1, a and b tick to 0, and c to m and d to n. We divide. Let q and r be the quotient and the remainder respectively as c divided by d. Remainder 0. If r equals 0, the algorithm terminates. We have in this case am plus bn equals d as desired. And then we do that swapping stuff, that recycling. Okay. If we suppress the variables a, b, a tick and b tick from this algorithm and use m and n for the auxiliary variables c and d, we have our old algorithm 1.1e. The new version does a little more by determining the coefficients a and b. Suppose that m is equal to, yeah. Okay. This answer is correct. Fine, 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 fine. The problem is to prove that this algorithm works correctly, properly for all m and n. It's getting very windy, isn't it? We can try to apply the method of mathematical induction by letting Pn be the statement. Algorithm E works for n and all integers m. However, that approach doesn't work out so easily and we need to prove some extra facts. After a little study, we find that something must be proved about A, B, A quote and B quote, or A tick, B tick, something like that. And the appropriate fact is that the equalities such and such, A tick M plus B tick N equals C and AM plus BN equal D, always hold whenever step E2 is executed. We may prove these equalities directly by observing that they are certainly true the first time we get to E2, and the step E4 does not change their validity. See exercise 6. Okay, great. Now we are ready to show that algorithm E is valid by induction on n. If m is a multiple of n, the algorithm obviously works properly since we are done immediately at E3 the first time. This case always occurs when n equals 1. The only case remaining is where n is greater than 1 and m is not a multiple of n. In such a case, the algorithm proceeds to set c to n and d to r after the first execution, and since r is less than n, we may assume by induction the final value of d is the GC greatest common divisor of n and r. By the argument given in section 1.1, the pairs m and nr have the common divisors, and in particular they have the same greatest common divisor. Hence d is the GCD greatest common divisor of m and n, and am plus bn equals d by 6. The italicized phrase in the proof above illustrates the conventional language that is so often used in an inductive proof. When doing part B of the construction, rather than saying we will now assume P1 through Pn, and with this assumption we will prove Pn plus 1, we often say simply we will now prove Pn. We may assume by induction that Pk is true whenever k is between 1 and n. It is a bit hardcore, isn't it? And then we've got these fun diagrams. If we examine this argument very closely and change our viewpoint slightly, we can envision a general method applicable to proving the validity of any algorithm. The idea is to take a flowchart for some algorithm and to label each of the arrows with an assertion about the current state of affairs at the time the computation traverses that arrow. See figure 4. Okay. It's interesting. Right. Okay. So he's producing a collection of like facts that we can prove to be true at each point in this algorithm. I think. See figure 4 where the assertions have been labeled A1 through A6. All of these assertions have the additional stipulation that the variables are integers. This stipulation has been omitted to save space. A1 gives the initial assumptions upon entry to the algorithm, and A4 states what we hope to prove about the output values A, B, and D. The general method constructs a proof for each box in the flowchart that if an assertion attached to any arrow leading to the box is true before the operation in that box is performed, then all the assertions on the relevant arrows leading away from that box are true after the operation. Thus, for example, we must prove that either A2 or A6 before E2 implies A3 after E2, sorry, let me clarify that in my head. Either A2 or A6 before E2, because those are the two routes into it. Implies A3 after E2. Okay. Yeah, so we kind of like each, I mean, this is going to be a lot of work, right? Like you need to be able to prove that for each step in this algorithm, the properties you want to be held after it are implied or you know, true after the algorithmic step, given the places that it can come from. Oof. Okay. In this case, A2 is a stronger statement than A6. That is, A2 implies A6. So we only need to prove that A6 before E2 implies A3 after. Notice that the condition D is greater than 0 is necessary in A6 just to prove that operation E2 makes sense. It is also necessary to show that A3 and R equals 0 implies A4, and that A3 and R is not equal to 0 implies A5, etc. Each of the required proofs is very straightforward. Once statement 7 has been proved for each box, it follows that statement 7 is improved for each box. It follows that all assertions are true during any execution of the algorithm. For we can now use induction on the number of steps of the computation. For we can now use induction on the number of steps of the computation. We can now use induction on the number of steps of the computation, in the sense of the number of arrows traversed in the flowchart. When traversing the first arrow, the one leading from start, the assertion A1 is true, since we always assume that our input values meet the specifications. So the assertion on the first arrow traversed is correct. If the assertion that labels the nth arrow is true, then by 7, the assertion that labels the n plus 1st arrow is also true. Using this general method, the problem of proving that a given algorithm is valid evidently consists mostly of inventing the right assertions to put in the flowchart. Once this inductive leap has been made, it is pretty much routine to carry out the proofs that each assertion leading into a box logically implies each assertion leading out. In fact, it is pretty much routine to invent the assertions themselves, once a few of the difficult ones have been discovered. Thus, it is very simple in our example to write out essentially what A2, A3, and A5 must be, if only A1, A4, and A6 are given. In our example, assertion A6 is the creative part of the proof. Assertion A6 is... Right, okay. All the rest could, in principle, be supplied mechanically. Hence, no attempt has been made to give detailed formal proofs of the algorithms that follow in this book at the level of detail found in Figure 4. It suffices to state the key assertions. Those assertions, which are often called inductive assertions because we prove them by induction on the length of computation, either appear in the discussion following an algorithm or they are given as parenthetical remarks in the text of the algorithm itself. This approach to proving the correctness of algorithms has another aspect that is even more important. It mirrors the way we understand an algorithm. Recall that in section 1.1 the reader was cautioned not to expect to read an algorithm like a part of a novel. One or two trials of the algorithm on some sample data were recommended. This was done expressly because an example run-through of the algorithm helps a person formulate the various assertions mentally. It is the contention of the author that we really understand why an algorithm is valid only when we reach the point that our minds have implicitly filled in all the assertions, as was done in Figure 4. This point of view has important psychological consequences for the proper communication of algorithms from one person to another. It implies that the key assertions, those that cannot easily be derived by an automaton, should always be stated explicitly when an algorithm is being explained to someone else. When algorithm E is being put forward, assertion A6 should be mentioned too. An alert reader will have noticed a gaping hole in our last proof of algorithm E, however. We never show that the algorithm terminates. All we have proved is that if it terminates, it gives the right answer. Notice, for example, that algorithm E still makes sense if we allow variables m, n, c, and d and r to assume values of the form u plus v root 2, where u and v are integers. The variables such and such are to remain integer valued. If we start the method with m equals 12 minus 6 root 2 and n equals 20 minus 10 root 2, say, it will compute a greatest common divisor 4 minus 2 root 2 with a equals plus 2 and b equals minus 1. Even under this extension of the assumptions, the proof of assertions A1 through A6 remain valid. Therefore, all assertions are true throughout any execution of the procedure. But if we start out with m equals 1 and n equals root 2, the computation never terminates. Hence, a proof of assertions A1 through A6 does not logically prove that the algorithm is finite. Okay, fine. Proofs of termination are usually handled separately. But exercise 13 shows that it is possible to extend the method above in many important cases so that proof of a termination is included as a byproduct. We have now twice proved the validity of algorithm E. To be strictly logical, we should also try to prove that the first algorithm in this section, algorithm I, is valid. In fact, we have used algorithm I. Now what is that again? Oh, it's the induction one. In fact, we have used algorithm I to establish the correctness of any proof by induction. If we attempt to prove that algorithm I works properly, however, we are confronted with a dilemma. We can't really prove it without using induction again. The argument would be circular. In the last analysis, every property of the integers must be proved using induction somewhere along the line, because if we get down to basic concepts, the integers are essentially defined by induction. Therefore, we may take as axiomatic the idea that any positive integer n either equals 1 or can be reached by starting with 1 and repetitively adding 1. This suffices to prove that algorithm I is valid. For a rigorous study of fundamental concepts about the integers, see the article on mathematical induction by Leon Henkin. The idea behind mathematical induction is thus intimately related to the concept of a number. Noteworthy early examples of inductive reasoning can be found in Sefer Masai Hoshev by Levi ben Gershon in France and Arithmeticorum Libri Duo. My Latin is not what it once was, and it never was much, by Francesco Marolico in Italy. Pierre de Fermat made further improvements in the early 17th century. He called it the method of infinite descent. The notion also appears clearly in the later writings of Blaise Pascal. The phrase mathematical induction was apparently coined by A. D. Morgan in the early 19th century. With a source, further discussion of mathematical induction can be found in Bollier's book Induction and Analogy in Mathematics. The formulation of our algorithm proving in terms of assertions and induction is given above is essentially due to R.W. Floyd. He pointed out that a semantic definition of each operation in a programming language can be formulated as a logical rule that tells exactly what assertions can be proved after the operation based on what assertions are true beforehand. See such and such and such. Similar ideas were voiced independently by Peter Nauer, who called the assertions general snapshots. An important refinement, the notion of invariance, was introduced by Hoare. See, for example, etc., etc., etc. Later authors found it advantageous to reverse Floyd's direction, going from an assertion that should hold after an operation to the weakest precondition that must hold before the operation is done. Such an approach makes it possible to discover new algorithms that are guaranteed to be correct, if we start from the specifications of the desired output and work backwards. See Dijkstra. And that would be an interesting thing to read at some point. The concept of inductive assertions usually actually appeared in embryonic form in 1946. At the same time as flowcharts were introduced by H. Goldstein and John von Neumann. Their original flowcharts included assertion boxes that are in close analogy with the assertions in Figure 4. See John von Neumann, collected works. See also A.M. Turing's early comments about verification. And figures. Interesting. We've got a quote. The understanding of the theory of a routine may be greatly aided by providing at the time of construction one or two statements concerning the state of the machine at well-chosen points. This is Turing. In the extreme form of the theoretical method, a watertight mathematical proof is provided for the assertions. In the extreme form of the experimental method, the routine is tried out on the machine with a variety of initial conditions and is pronounced fit if the assertions hold in each case. Both methods have their weaknesses. How interesting. How interesting. Didn't Knuth also quote this one? I guess he's quoting it right now. But maybe that's not what you mean. Okay. Now, how long have I been on for? About 2 hours. Yeah, no, we're actually in the art of computer programming at the moment. Yeah, so I suppose it's kind of, if you come in halfway through, then you might think I've just gotten to the induction chapter in Book of Proof, but I haven't. I thought I probably knew roughly enough about proof to revisit this chapter and see how much I understood. I don't think we're totally done with it, but I felt like trying my new understanding against it. Okay. We're gonna take a little break. Wow, I've lost 3.6% of the frames. That's so many frames. What have you all been watching? Okay. Now, I'm going to take a short break, and I'll be back in a couple of minutes. Until then, and I was, of course, going to do these exercises, see how many I can get through. Until then, enjoy some space. Hello. Oh, my little dissolvey, aren't I? Maybe I can sort that out. Nope, that's worse. There we go. I think that's better. Okay. So, we haven't had any dropouts for a while, so maybe I can stop listening to my own voice for a moment. Okay. Wow, blurred as well. Okay. So we got some exercises. I've done some of these before, though not all of them. So, let's work through them and see how we do. That's enough of that, please. Now, number one. Explain how to modify the idea of proof by mathematical induction in case we want to prove some statement Pn for all non-negative integers, that is n equals 0, 1, 2, etc. instead of for n, 1, 2, 3, etc. So we could, in that case, we could prove P0 right? Then prove that if it's like, how do we frame this? If P0 through Pn is true, Pn plus 1 is true. I think that's right. Let's see, actually. That's kind of a more, probably a slightly more formalized way than I put it last time. Let's find out. For all n is greater than 0. Greater than or equal to 0. Okay, so that's the bit I missed. Okay, cool. Right. Now we get onto the real problems. Now this is the one I was puzzling away at before stream to see if it was time for me to move back into this again. And okay, temperature's getting lower. That's good. And I decided it was. So the problem reads, there must be something wrong with the following proof. What is it? Theorem. Let a be any positive integer. For all positive integers n, we have a n minus 1 equals 1. That's the theorem. Let a be a positive number. For all positive integers n, we have a to the power n minus 1 equals 1. Proof. If n equals 1, a to the power n minus 1 equals a to the power 1 minus 1 equals a to the 0th power, and that equals 1. And by induction, assuming we have the theorem, assuming that the theorem is true for 1, 2 through to n, we have a to the power n plus 1 minus 1, which is equal to a n, which is equal to this thing, which then works out to be this, which then works out to be this. We've got the special term b here, which turns out to be, which should be this. So the theorem is true for n plus 1 as well. Now, the correct answer here is that there is potential division by 0 in here. But this stumped me for a while. I was like, oof. I mean, I kind of get the spirit of the proof, but I don't really, not really sure I can capture it. So the approach I took is, after sort of puzzling away at it, I identified that this step was a trouble for me, and this step was a trouble for me. So I had a kind of, I think I had a hunch / I looked forward to the answer and saw that this, you know, a division by 0 is likely to be the issue here. And that kind of got me to the point where I could start to scrape away at it. Now, this issue, let's call this Q. So, again, I did what I did in the last example that we worked through, which is I took this kind of equation here, and I tried this formula here, and I tried to reduce it to an, and so I'm going to do that now, just so that I capture it, and also extra practice, I suppose. So we've got an minus 1 multiplied by a n minus 1. What am I doing here? 1 over b, delightfully devilish, Seymour. Yes, yes. And this is supposed to turn out equal to a n, and b is like some wild thing over here. So b is a, and then I'm going to put this slightly differently, n minus 2 over n minus 1. Now, this is like horrible, and I was looking at this, I was like, how on earth, like, what possible rule could you use to go from this to this? And turns out there is none. He just did it. He just did it, right? He was like, it's the same thing. And it is the same thing. And we could show this ourselves as well. So first thing I'm going to do is I'm going to take this box here, and I'm just going to open it up a bit. So we've got bn minus 1. It's amazing this is a computer, one of the big computer science texts. But wow, I'm really losing my lighting here. Not good. Okay. Is this better? It's still going to dissolve slightly, maybe. Oh well, that's what being a hologram is. Okay, so we get this. Sorry, n minus 1. Great. So this turns out to be sorry, my keying is just bugging me. I think it's okay. I think it's alright. It's okay. Anyway, this bn minus 1 actually is, and I think this is part of what makes it slightly trickier to spot, because otherwise it would simplify out kind of easily. A to the power n minus 2 over n minus 1, and all of this to the power n minus 1. Now, if you are raising something with a power to another power, you can multiply them, multiply the exponents. So you can then put this in terms of n minus 1, put that in brackets there, multiplied by n minus 2 over n minus 1. Now we've got something divided by n minus 1 multiplied by n minus 1. So we can simplify this to a n minus 2. Now, so this ends up being a n minus 2. Now, so here's where the problem comes in. The problem is terrible keying. What is going on? Awful. The problem is that, so we've proved this for n equals 1, right? If we have n equals 2, on the face of it, this thing, there's nothing in here that says that this should end up being 0, because if n is 2, n minus 1 is just going to be 1, right? So it's fine. But what it actually simplifies out to is a to the power n minus 2. Does this even work, actually? I don't even know if this works. No, wait. I've lost it. So irritating. A is any positive number. Yeah. Okay. N minus 2. Got the case where n equals 1. Well, this might even work, actually. What am I? Let me work this through and see where I get this. We then get what have I done wrong here? We then get, in the case where n is 2, we then get this potentially being a to the power 0. Now that would be 1, which is sort of fine to have on the bottom here, right? This isn't actually what I did, I don't think. Now I think of it. Huh. I really thought I was onto something there. Maybe I made some sort of mistake somewhere. Let me check my thinking. Okay. Great, so we get from bn minus 1 now b is going to be this, that we know. A is a positive integer. N is, let's say n is 2. We end up with a to the power 0 over here. Okay. Where have I gone wrong here? I had it earlier. So annoying. Oh no. Okay, well anyway, let me continue with what I was thinking of, where I went with this earlier. Maybe it'll come back to me. So we end up with this. I mean, it'll at least correct, see if I have any mistakes. So let's say we end up with a n minus 2 here. Fine. So then we have, after all of this, a n minus 1 multiplied by a n minus 1 over a n minus 2. Now, if we do this, if we work this out with the kind of exponents again, we're multiplying these two together, so we actually end up with, focus on the top half, we end up with a n minus 1 plus n minus 1, because they're multiplied, we can add them. This then simplifies out to be 2n. Let me just sort this out in my mind. 2n, so we've got 2 n's here, minus 2. So that's 2n minus 2. And then we've still got our n minus 2 on the bottom. Now when we're dividing, we can subtract the exponents. So we end up here with a 2n minus 2 minus n minus 2, which is going to end up being a 2n minus 2 minus n plus 2. Now if we look at this, we can see that this ends up being this 2n, so we collect the n's, we've got 2n minus n, so that's going to be n. And then we've got minus 2 plus 2, and so we've got a to the power n. So we've got this. So that's how come this works. Now, after this, we've got this additional step here. I didn't think I felt I needed to look at this one, but let's look at it now. Yeah, now the reason this works is because we're assuming that the theorem is true. This kind of befuddled me earlier for a bit. We're assuming that the theorem is true. Now, given that we're assuming the theorem is true, and we've already got, they're already assuming this theorem, right? Then we can substitute in for a n minus 1 here. We're going to substitute in for the ones on the top. 1 and 1. So a n minus 1 gets substituted in here, right? And I guess the logic is that we should also be able to do it here, because b ends up having to be also a positive number. So we're also having to assume that this is a positive number. And can we assume that? Can we assume b is a positive number? Well, b is a n to the power minus a to the power n minus 2. We can't really assume... I don't think we can assume that. I don't think we can assume this is a positive number, because let's say in the case where we've got... what should we call it? Let's say P... Let's say in the case we've got P... We've sorted out P1. Let's say we're moving on to P2, and we're trying to rely on the fact that an minus 1 is going to be positive. Is that anything? Is that anything? Well, it's a bit suspect, isn't it? Maybe that's the problem. Like, yeah, maybe it's the problem. Maybe the problem is that we can't use this. Now, I happen to know, essentially the answer is there's a possible division by 0. And earlier it felt, I think I made a little bit of a leap here, which isn't true, that we can end up with B. So we can end up with... No, actually. I think I get it. I guess we need to not... Yeah, we need to be considering this case, maybe? Yeah, so what's this proof? Well, what's this? We've got n equals 1. Fine. By induction, assuming that the theorem is true for 1, 2 through n, we have that this whole thing. So I guess this has to be true for n equals 1. And in the case where we've got in the case where n is 1, we would have this term, which is on the bottom of this division here. We would have a1 minus 2, which would be a minus 1. A minus 1 is... I guess 1 minus 1, 2 minus 1, 3 minus 1. Well, okay, this is kind of messy, actually. So, to the power minus 1 is like 1 over. So we'd have 1 over a. And the bigger a gets, the smaller this number gets. Is that enough for it to get to 0 and therefore break this? Or is it this division by 0, maybe? Even though we kind of get rid of it. Is this the problem here? Because if n is 1... then... of course, this is going to be 0. So in this case, we get, well, -1 maybe over 0. Even though we do get rid of it, I guess we can't have it in there at all. So maybe this would be the issue. Okay, let's see what Knuth says. Sorry, I know you're probably screaming in the chat right now. I just wanted to puzzle through this one. Okay, the formula for B, so it is the formula for B, involves division by 0 when n equals 1. Therefore, the theorem is not improved for n plus 1 equals 2. Okay, so it's the formula for B that's the issue. So actually, I had that a bit wrong earlier. Yeah, so I had that a bit wrong earlier. The formula for B involves a division by 0. Still, I had to work through a bunch of this to satisfy myself any of this even worked at all. Okay, so it's the formula for B that's the issue. And so it's got to be this. It's got to be this thing here that's the problem. So where n equals 1, we end up with 0 on the bottom here. So that's the kind of issue. Okay, interesting. Well, there you go. Kind of simpler, different than I thought it was, but still explicable to me, which is good. Exactly. B is not well defined in the case n equals 1. Thank you, Bubbledon. Okay. All right. Still some progress. Let's look at number 3. Difficulty 18. The following proof by induction seems correct, but for some reason the equation for n equals 6 gives 1/2 plus 1/6 plus 1/12 plus 1/20 plus 1/30 equals 5/6 on the left hand side, and 3/2 minus 1/6 equals 4/3 on the right hand side. Can you find a mistake? Theorem. 1/1 by 2 plus 1/2 by 3 plus whatever up to 1/n minus 1 times n equals 3/2 minus 1/n. Proof. We use induction on n. For n equals 1, clearly 3/2 minus 1/n is equal to 1/1 times 2, that's 1/3. No, sorry, 1/2. And assuming that the theorem is true for n, assuming the theorem is true for n, 1/1 by 2 through this thing. So he's adding this term here, maybe. Presumably he'll be adding it to both sides. Is he adding it to both sides? Yes, he is. He's adding it here as well. Okay. Equals... Okay, so he does this. He's got the other side as well. And then he's setting this up 3/2 minus 1/n plus 1/n, yeah, minus 1/n plus 1. What has he done there? Oh, okay. Died again. We're about to get a glitch. I can feel it coming on. Yep, there we go. Such a weird glitch. Gosh, I've got to figure this out. Okay. Come on, come on, come on. There we go. Back there, back here, back everywhere. Okay, am I audible? Yes, I am. Great. Okay, got to sort that out. Alright, so what is he doing here? He's got... Oh, funny bird noise. We use induction on n. For n equals 1, yeah, fine. And assuming the theorem is true for n, we try to prove that it's true for n plus 1. So he takes the formula for n and he adds this to both sides. We've got that here too. Then he does something with the right hand side, which involves transforming this into this somehow. And then he has then he somehow transforms it into this. So the steps I'm a little confused on are this one and this one. It'd be good to just work through those so I can understand what's going on there, even if it's not really relevant. I guess he's dealing with the he's probably... So this one we can maybe look at. Let's call this one Q. Let's look at that. Let's see if we can work out how he's doing that. Okay, so he's got 3 over 2 minus 1 over n plus 1 over n minus 1 over n plus 1 equals 3 over 2, that's fine, minus 1 over n plus 1. Now, if we take the left-hand side, what can we do with that? Collect some terms, maybe? Ah, okay, these cancel each other out, don't they? So it's 1 over n plus 1 over n minus 1 over n plus 1. Glitching out again, aren't they? Okay. And then these cancel each other out. So we've got 3 over 2 minus 1 over n plus 1. And that is going to be the same as it's going to be the same as this for n plus 1. So I don't know if we get to use p for this, but let's say like p n plus 1. You get the idea. Okay, that makes sense. Now what about this other step? Just learning algebra from Knuth here. Alright, so that one, okay, I'm satisfied. Let's try another one. Let's try the other side. Okay, well, let's not call it P, let's call it S. This is kind of hard to draw. Okay. Now, these two terms are the same. So we don't need to worry about those. We basically need to show that this thing here is equal to this here. If indeed it is. Of course, we know there's a mistake in this somehow. It would be odd if it was just an algebra mistake, I suppose, but... But let's try and just perform 1 over n minus 1 over n plus 1. And we can find out what this gets if we actually try to put this as one equation. Now, in that case, we want to get the terms on the bottom, whatever they're called, to be the same. So we can cross multiply, I think. I think that would work. So we want to have n plus 1 on the top of this term over n. Sorry, n plus 1. And then we want to subtract this from n over well, it'll be n over n plus 1 again. Sorry, not plus 1 there. No, it will be actually. Now, given they've got the same term on the bottom, it's quite clear we're going to have 1 on the top because we're going to be subtracting this n away. Yeah, so we can just do that straight off. Yeah, it's 1 over n plus 1. Okay, cool. So that's exactly what we've got here. Fine. So those, yeah, I mean, it was never going to be an algebra problem anyway. But there's some sort of mistake. We can plug in an example. We can plug in the example maybe. That might help us find it. Is there anything obvious like a division by 0 here? Okay, the theorem is 1 over 1 by 2, or 2 over 1 over 2 by 3, etc. So there shouldn't ever be a 0 on the bottom. Well, maybe, actually. This is a little suspect, isn't it? But that's the theorem, right? So I don't know if we care about that. We know n is going to be 1 or more. Yeah, so I don't think it's that. Well, let's try plugging in 6 and see what we get. Now how do I... Yep, there we go. Give myself some extra room. Okay. N equals 6. Okay, 1 over 1 by 2, that's 2, plus 1 over 2 by 3, which is 6, of course. Then we've got 1 over 3 by 4, which is going to be 12. Then we've got 1 over 4 by 5, which is going to be 20. One over 5 by 6, which is going to be 30. And then that works out to, I guess it works out to be 5/6, as Knuth says. And on the right hand side, we've got 3 over 2 minus 1 over 6, which is going to be 4 over 3. Could the problem be in n equals 1? We haven't spent that much time on that. So if n equals 1, then we've got one over 2 and we're saying this is equal to 3 over 2 minus 1 over 2. Sorry, 1 over 1. So yeah, that's going to be 1/2. This one delightfully devilish too, you're thinking, Bubbledon. It's feeling a little devilish. Okay, so n equals 1 seems true. Assuming that the theorem is true for n, we try to show that, yeah, so assuming that it's, yeah, so if we try to put this in terms of induction, we want to assume that the theorem is true for n equals 1 through n. More specifically, it's true for n. And then we want to transform that into something that shows what n plus 1 is. You know, I guess we could try it out with n equals... We could try it out, actually. Here's an idea. We could try it out with... let's just actually get rid of all this. Let's try it out with... Let's try out all this process with n equals 5. That should be illustrative, right? Because if it's true, all of this should work. And we know it's not true. Or at least we should actually check that n equals 5 actually does work. So does the formula work for n equals 5? Okay, so 1. Just do a quick check of this. 1/2 plus... Yeah, I mean it's going to be the same sequence, right? And this equals oof. I don't know any quick ways of doing this. Guess you could multiply them. I'm sure there's a trick, right, you can do with this. Let me see if I can do it the hard way. This will become 10 over 20. This will become 6. Oh, it's annoying. Okay, whatever. I'll just try and calculate it. 1 over 2 plus 1 over 6. Should know how to do this, really. Now that comes out to be 0.8. What's that in 20ths? Well, that's 4/5. Probably. Yeah, so let's say that. And then the right-hand side, that's going to be 3 over 2 minus 1 over 5. Now that is not true either. Because for that we get, well, we get 1.3, which is actually going to be, ugh, it's so annoying. Okay. It's like 3 by 5 over 10 minus 2 over 10. That's 15. And so we've got 13 over 10. which is what I get. Yeah, fine. Okay, so it doesn't work for n equals 5 either. Assuming I've not made any horrible mistakes, which I don't think I have. Half, 6th, 12th, 20th. Okay, well, let's keep going then. N equals 4. 1/2 plus 1/6 plus 1/12. That's going to be this one I can do by hand. That's going to be 6/12 plus 2/12 plus 1/12, which is going to be 6, 8, 9. 9/12, which is 3/4, right? So that's 1/2 plus 1/6 plus 1/12. That's 3/4 indeed. Okay. And then I need to get this stuff off my screen. Okay. Right, and then we've got 3/2 minus 1/4. And that is going to be 6/4 minus 1/4. No, that's not right. What am I doing? That's going to be 3/4. Wait, what am I trying to do here? 6/4. Yeah, because I'm doubling them. I'm trying to get up to 4. Fine. Yeah, I don't know what I'm doing. Okay, 1/4, which is going to be 5/4. Patently not the same. Okay. Does it work for anything? Let's try n equals 3. One half plus 1/6. So that's 1/2, 2/3. And that's that. And that's going to be 3/6 plus 1/6. That's 4/6, which is going to be 2/3, right? Yep. Okay, and then we've got 3/2 minus 1/3. That's going to be 9/6 minus how many? 2 sixths. 8 sixths. No, wait, I'm doing all this wrong, aren't I? 9, 8, 7. Over 6. Also not right. Unless my arithmetic or fractions are just completely bogusly wrong. Okay, let's keep going. My arithmetic's fine. Thanks for the check, Bobadon. I appreciate it. Okay. Well, this one, we won't, at least won't have to check it anymore. It's like reverse induction. Okay, so with this one, we've got 1/2. Of course, and then we've got 3/2 minus 1/2 is 2/2, which is just 1. Obviously not the same as 1/2. Okay, so it doesn't work for any value of n that we, at least, that we've tried so far. Okay, so, well, let's try it with real numbers then, going from just trying it with n equals 2. So, yeah, let's take it from n equals 1 to n equals 2. So, we've got 1/2 equals 3/2 minus 1. Let's go with 2 here. Just remember n is 1. Oh, it's 1 actually. Sorry. Yeah, okay. That works. Yeah, and then we add to the right hand side. So we're dealing with the right hand side. Minus 1/1 plus 1/1 1 plus 1. And that's going to be 2. Okay. And then we do 3/2 minus 1/1 plus 1/1 minus 1/1 plus 1. And this should equal 3/2. Hello, Fook Life 108. How you doing? One over 1 plus 1. So somewhere in here, there's a mistake. How do we compare this to what we got out of n equals 2? Right, so we get 3 over 2 minus 1 over 2, as we should, from n equals 2. But it doesn't add up to what the sequence gives us. Actually, I did this slightly wrong here, didn't I? I omitted something in it. Yeah, I omitted this sort of part. Yeah, let's go back to that. Could be one of those later steps is wrong, but I just want to clarify this. Okay, so we're on n equals 1. We know this works. Let's not even worry about this, actually. Let's take this left-hand side. We've got... Wait. That shouldn't be there. N equals 1. The actual series, right? It should be... We're sort of being tricked by this. It should end at 1 over 1 minus 1. One. So it shouldn't... I mean, this is going to be, you know, 1 over 0, so that's not right. So this... So it's like clearly right. It's giving us this. It's saying like... Clearly, 3 over 2 minus 1, sorry, minus 1 over n equals 1 over 1 by 2. But 1 over 1 by 2 is actually the first term for when n equals 2, because this is the term for when n equals 6, and it ends with 5 times 6, right? So n equals 5 should end with 4 times 5. N equals 4 should be 3 times 4. N equals 3 should be 2 times 3. N equals 2 should be 1 times 2. N equals 1 should be 1 times 0. And that's not right. So he's sort of using... He's got this bit muddled up. Yeah, and this expansion is like slightly hiding the fact that this 2 is only valid for when n is greater than or equal to 2. So none of this works in the case where none of this is really valid in the case where n is equal to 1. Like this expansion would just be nothing because there's no terms in it. Okay, I think that's possibly the answer. Ah, Bubbledon, yes. You're saying what I just said, but probably I assume earlier. Yeah, okay, so the n equals 1 cases. I should have known when he said clearly. I should have known. Okay. Yeah, it's also not true. So that's also a mistake. Alright, what does Knuth say? Oh yeah, got to click the right place. Knuth says, so the correct answer is 1 minus 1 over n. The mistake occurs in the proof for n equals 1, when the formula on the left may be assumed to be meaningless, or it may be assumed to be 0, since there are n minus 1 terms. Okay. Well, that's roughly what we got to, right? Okay. Exciting stuff. Ah, that's what Foucault was saying, but in more mathematical terms. Here n equals n minus 1. Yes, that's right. Ah. I understand what you were saying now, Foucault. Ah. Right. What time is it? 7. Let me read number 4 anyway. 20. Prove that in addition to equation 3, Fibonacci numbers satisfy Fn. So the Fibonacci term n is greater than or equal to phi n minus 2 to the power of n minus 2 for all positive integers n. Okay. That sounds like a bit of fun. I don't know if it's fun for today or not. I think it's probably not fun for today. Maybe I'll start it. I'm tempted. I have other work I have to do today, unfortunately. Pre-Monday work. You know, it's getting bad when you've got, like, pre-Monday work to do. Presumably we have to use that equation again. Or we might have to use something a bit different. I guess we'll find out. Whoa, I went too far. Wow, this looks crazy. What is he doing? Knuth, no, what are you doing? What is all this about? Okay, alright. Exciting. Okay. I think we will leave it there. I'm gonna I don't think I will think about this one actually offline, but just because it's a bit complicated for my brain at this point. Just curious about looking at some of the others. Prime number is an integer. Yeah, this one gets they get harder. We get some 20s, some 23s, some 25s. We get some mathematical ones. It's funny that these are the non-mathematical ones. And I guess we have to... They come in 3 levels. They've got like mathematical and then higher mathematical. For mathematically inclined learners, I think. And then we've got some algorithm proving to do. Oh my gosh. Okay, these get quite fun, don't they? We've got a 50 here. We've got a 50 difficulty problem. All right, let's read the 50 difficulty problem from R.W. Floyd. So 50 means it's unsolved, I think. Prepare a computer program that accepts as input programs in some programming language together with optional assertions, and that attempts to fill in the remaining assertions necessary to make a proof that the computer program is valid. For example, strive to get a program that is able to prove the validity of algorithm E, giving only assertions A1, A4, and A6. Ooh. Oh, exciting. Prepare a computer program that accepts as input programs in some language together with optional assertions, and that attempts to fill in the remaining assertions necessary to make a proof that the computer program is valid. So it's like a generic prover of any program in, I guess, in a special language. Well, that would be quite an accomplishment. Okay. Page 28. Okay, then we get like all kinds of crazy stuff. And then only after that do we get to move on. Obviously, I'm going to do all the exercises 100%, right? No, not going to do... That's not the kind of textbook this is. Okay, exciting. Exciting stuff. This has been fun. It's been a fun session today. I'm glad to have applied some stuff. I am from the UK, Fook Life. For my sins, as they say. You're welcome to congratulate me on the part I played in beating Norway yesterday, which was no part at all. In the World Cup, I mean, not in general. Okay, let's see who's on the raid potentials today. Very game focused, as always. Oh, we've got someone who's doing capture the flags. That should be quite exciting. Wow, actually we've got like quite a few interesting streams today going on. We've got someone doing railroad diagrams. That I would kind of like to watch. Okay, I think we're gonna take a look at the smaller streamer. Still bigger than what we're doing here, I think, but smaller. All the British players are watching my stream. Yeah, that's what motivated them. They were like, we've got to do this for K. Okay, we're raiding. We're raiding through. This should be interesting. Interesting stream to go raid. Okay, let's go. England played well, thank you. All right, we got a few seconds left. I will be back on Thursday. I will be streaming then, so I'll see you for more of this on Thursday. Bye.